Okay, so last time we just finished the section of statements. We talked about different aspects of statements from the definition to compounded statements. Um, you know, we we talk about the prediction and the tautology at the end of that section. In this section, we're gonna talk about open sentences. So open sentences are different from statements in that an open sentence does not give you a truth value. A statement must have a truth value in any case. So that's the difference. Open sentence, that means you don't have an answer for it. It doesn't give you whether it's right or not. But a statement must be either true or false. Okay. So what is the statement? Statement sentence, open sentence, I'm sorry. What is an open sentence? An open sentence is a declarative sentence containing one or more variables that when all of the variables are assigned values in the respective domains, the resulting sentence has a truth value. So not only an open sentence does not have a truth value, but also it has some variables, maybe one variable or more variables that if you assign values, specific values for those variables, then it should become a statement. So it needs to give you a truth value. So that's the only difference. In other words, in the open sentence, you have variables. Or if you just change the numbers, for example, in the statement to a variable, then it becomes a sentence. All right, that's the definition. So for example, let's just see some examples to understand the concept of open sentence. So in this example, let x and y be variables, so they can be changed. You don't know what they are if you just write the x and y. And they're both real numbers. So then you can define an open sentence p of x and y as x greater than y. So this is what it means. So this open sentence p of x, y is the same as x greater than y. So this is an open sentence. It's not a statement because we have two variables, x and y, that are not assigned any value. Okay, but if you change those variables to specific numbers, then it becomes a statement because you can tell whether it's true or false. So so if we write p of 2, 3, that means x equal to 2, y equal to 3, then the open sentence x greater than y is just becoming 2 greater than 3, which is false. Okay. Or if you plug in 5 for x and 2 for y, you write a p of 5, 2. Then there is also a statement because 5 is greater than 2, right? Okay. So you see the difference in notation. In the notation of open sentence, you have variables x and y. Okay. But if you change these variables to numbers, then it becomes a statement. And previously, if you still recall, we just use P, Q, or whatever T, those capital letters to denote a statement because it does not have variables. So you don't need to write these parentheses at all. But just use P to denote a statement. For example, then you can tell whether it's truth value is true or false for this statement. But since open sentence has some variables, then you have to specify. You have to write these variables explicitly with the notation P. When people know you are talking about the open sentence, all right? In other words, without anything, you just write P, then people know you're talking about the statement. All right. So so one thing is you have to plug in the numbers or values of xy from the domain of xy, or real numbers in this case, but you cannot plug in any other things. Okay, that's obvious. For example, if you write P parentheses apples, oranges, press back, and that doesn't make sense because that essentially means apples greater than oranges, and that doesn't make sense. You know, you don't know what it means. Apples greater than oranges, or you're talking about the size, or you're talking about price or whatever. You know, it doesn't make sense. Okay, so that's for the notation. Let's just do another example. So in this example, we're talking about triangles, and we let the S be the set of triangles. So that's the set of all the triangles, S. And let X be a variable with domain S. What it means is X is just one of those triangles. Okay. So then we can have a define open sentence P of X as the sum of the interior angles of X is 180. So that's an open sentence because it has a variable X. And the open sentence itself says the sum of the interior angles of X is 180 degrees. And we call this P of X. So the X appears in here. All right. Okay. If you let X be any value or any element of S, okay, then it means X is a triangle. X belongs to S, so that X means a triangle. So then you plug in that any triangle for X, and they say the sum of the interior angles of any triangle is 180 degrees, and that's true. So that's a statement, okay? So the statement that P of X, and the open sentence P of X, I'm sorry, happens to be true for all charts of X belonging to S. And it's a theorem, actually, as you know it from trig, right? Okay, let's see. You can also write another open statement, the Q of X. And that's the open statement is one of the angles of X is a right angle. So again, you know, X is an element in S. So X is just one of the triangles. So in that case, then the open statement becomes open sentence becomes a statement. I'm sorry, I keep saying that statement. So once you specify X as an element from the set S, it means you are talking about a triangle. Okay, so one of the angles of any triangle is a right angle, and that's not true for all of the X belong to S. So for all the triangles you cannot say, one of the angles of the triangle is right angle, of course. So that's not true. All right. So for this statement to be true, the x has to be a spatial triangle. We call it the right triangle, right? As you know. Okay. There's one thing that needs to take spatial attention. An open sentence is much like a function from calculus, so because it is a variable, right? And when you plug in any specific value of x, it gives you a truth value. So that's the only difference, instead of given a actual value or number in normal functions, you get the truth value in this case, but they're similar. Okay, even if an open sentence is true for each value, but the variable, it does not become a statement. Okay. So if you don't specify the value of the variable in the open sentence, then it's not a statement. Although, the open statement may be true for each of the value of the variable in the domain. It's still an open statement, not open sentence. I'm sorry, not a statement. All right. For example, if you write this open sentence, p of x, which is x squared greater than -1. Okay, and x is any real number. Okay, so this is an open sentence because you don't specify any value of x in this notation. Of course, we know the square of any real number will be greater than or equal to 0, so it'll be greater than -1. So this inequality always holds for any value of x. But this is still not a statement. It's still open sentence because you don't know what x is. To be a statement, there should be no variables. Okay, everything has to be definite. All right. So it's just like a function, when you write the fx equal to 2, it doesn't mean that the function f is equal to the number 2. That's just a notation. It's just a rule. Okay, so same in here. All right. So in the case of the open sentence, x squared greater than -1, I still rule that assigns the truth value to every real number. Okay. So in other words, you need to plug in a specific value of x for it to become a statement. Okay. So this is something that should be very careful when we talk about the open sentence. So let's see some more examples. Let's just come back with the example of triangles. So again, x is a variable with domain the set of all triangles. So it means x is just a triangle, okay? And then we already defined the two open sentences, px and qx. And px is the sum of the angle of x is 180, all right? And the qx is one of the angles of x is a right angle. Okay. So if we plug in a specific right triangle T in place of x, then the statement P of T intersecting Q of T or what do we call it in logic? Conjunction, Q. This is true. Okay, so so look at this compound statements. Since you specify this T a right triangle from the set of all triangles. So if T is a specific right triangle, you plug in, then both P and Q become statements. Okay, and both are true because P is always true for any triangle, and Q is true if the variable takes value of right triangle. Okay, so then you take the conjunction. It's true. All right, but if you plug in another value of x or another type of triangle, then Q may be false. Of course, P will be always true for any specified triangle, but Q is not. For example, if take a equilateral triangle and you call it E, so E is a specific equilateral triangle, not any arbitrary. That has to be one of those. Okay. Plugging P of E is true, and Q is false because now this time X is E, which is a specific equilateral triangle. We know in an equilateral triangle, there's no angle with 90 degrees. So Q of A is false. Then you take the conjunction of P and Q of E is false. All right. So pretty simple, it's just like a function. Okay. The difference is this time you get truth value instead of a numerical value. In the case of open sentences. So let's talk about some more examples. In this example, let x be a variable with domain the several real numbers. So x is a real number. We define two open sentences, P of x and Q of x, where P of x is defined as x greater than 3. So that's an open sentence. If you specify the value of x, it becomes a statement. It has a truth value in that case. Similarly, Q of x is defined as this open sentence of x less than 5. Okay, so then we can compound the open sentence just like statements, of course, because the only difference is you have variable now, but you can still take the compound open statements in each case. So we have 5 compound open sentences in here. We can take conjunction of P and Q, Px and Qx. We can take a disjunction of Px and Qx, or we can make a conditional open statement from Px to Qx, or by I don't remember how it calls, but this back conditional maybe from P of x and Q of x of open sentences. And the last one, is another compound open sentence with two operations, negation and conjunction of the two open sentences. Then you want to see, you want to know when each of those compound open sentences is true. Okay, we know we got the 5 compound open sentences, and we want to know whether when each of them is true, what a value of x makes each of the compound open sentence true. All right, let's just look at one of them, and you can work out, the remaining. So now we want to write a set of places. These statements are true. What value of x? In here x is a real number, so we want to know what values of x make the statements true. All right. Of course, when you specify the value of x, it becomes a statement, not the open sentence anymore. All right. So that's what it means in here. Let's just look at number 3. The compound open sentence 3 from P of x to Q of x. So that's a conditional open statement. And we have shown that, this is equivalent to negation P of x, disjunction Q of x. If you remember the equivalence of statements, okay, so for any specified value of x, this becomes a statement. So that's equivalent to this statement on the right. But when x is not specified, then we're talking about 2 open sentences, but they are also equivalent because for every value of x you plug in, this is true. They are equivalent. So these 2 open sentences are equivalent also. All right. So then we can use this equivalence open sentence to determine when the compound open sentence on the left is true. Okay, so then why that becomes a little easier to work out, whenever you have some conditional open sentence or conditional statement, it's a little hard to work out directly. Instead, you want to, make a little change for this, or change it to an equivalent open sentence to work with. So we got the negation of P of x, disjunction with Q of x, and that is easy to work with. Remember P of x is x greater than 3. Okay, so negation of it, that means x not greater than 3. So that means x is less than or equal to 3, or from negative infinity to 3, including 3 itself. And then Q is x greater than less than 5, I believe. Yes, Q. Or you can write in set notation as from negative infinity to 5, not including 5. And then you just take the disjunction of these 2 open sentences, right? Okay. So, by disjunction, if you specify any value of x in P of x and Qx, so then they become both become statements. Then you are talking about the disjunction of statements, and for disjunction of 2 statements to be true, then either of them has to be true. Okay, then we are considering when the negation of P of x is true and when Q of X is true. And we know when X is less than or equal to 3, P and negation of P of X is true, and when X is less than 5, the Q of X is true. So then, so either X is from negative infinity to 3 or from negative infinity to 5, then the compound statement now becomes statement. If you take a value from each of those intervals, then the compound statement is true. Okay. So translating this into union, right? Disjunction. That's either or all. So that means in terms of numbers, that means the union. Okay. Of these two sets, and it's from negative infinity to 5, it turns out that's the answer. So the third open sentence is true when X is less than 5. Of course, you know how to take the union of two intervals. One of the easy ways to work out these unions is to draw number lines. Okay, so using the number 9 to represent the intervals, and you're going to see the second interval from negative infinity to 5 actually includes the first interval. Or this first interval is a subset of a second interval, so the answer will be the second interval. All right, and you can easily work out other cases, and these are the answers. This is the answer. Okay. For example, if you try to work out the first open sentence, you want to know when this open sentence is true. So in that case, we are taking the conjunction. So for any specific value of X, we want both P and Q to be true, for the compound open sentence to be true. Oh, the statement, I'm sorry. Then, again, we know P of X is true when X greater than 3, and Q of X is true when X less than 5. So you take the conjunction of those two open sentences. That means you are taking the intersection of these two intervals. All right. Both have to be true. All right. For the whole thing to be true. Okay. So then, so obviously, X has to be greater than 3 and less than 5. So that's the first compound open sentence. When it's true, then X has to be between 3 and 5. And the second one, you just take a disjoint of these two open sentences. So for any specific value of X, for this disjunction of P and Q to be true, then either P or Q must be true. So that means, X has to be greater than 3 or less than 5. So you are taking the union of these two intervals, and if you draw the sets on the number 9, then you see the union of those two sentences is all real numbers actually. So that's the answer for the second open sentence. Well, we just worked out number 3 and number 4. We already worked it from the one side. We can work out from the other side, So we already worked P to Q. Then you need to work out from Q to P also, and then take the intersection of those X values from the two ways conditional open sentences. All right. For the compound open sentence to be true in number 4, and then you have to do both of them take the intersection, and turns out the answer is from 3 to 5. Okay, if you work it out, and again, you work out in the same way. So just like we did in number 3, from px to qx, you can just swap p and q. So it's from qx to px. So that's equivalent to negation of qx disjunction with px. And qx, is true when x is less than 5. So negation of it will be x greater than or equal to 5, right? Yes, greater than or equal to 5, and what? Q is true when x is greater than 3. So you take the union of x greater than 3 and x greater than or equal to 5. So if you do that, you actually get x greater than 3. If you draw the two open intervals on the number 9, and you see that x greater than or equal to 5 is a subset of x greater than 3. So the union of those two is x greater than 3. So that's from Q to P, and we know from P to Q, the statement's true when x is from -infinity to 5, and from Q to P, we just got the x greater than 5, right? X greater than 5. It's greater than or equal to 5, I think. Oh, x greater than 3. I'm sorry, x greater than 3. So x greater than 3. Take the intersection with that, and x less than 5 from P to Q. So from P to Q, we got x less than 5. Then the compound conditional open statement is true, but from Q to P, then x must be greater than 3 for the compound statement to be true. So if you take the intersection for those two, from -infinity to 5 and from 3 to +infinity, then the intersection is just from 3 to 5. So that's why number 4 is from 3 to 5, nothing including 3 and 5. Okay, obviously. And the last one is pretty straight. That is, you take the conjunction of negation P and negation Q. So in order for this compound open sentence, when you plug in a specific value of x, becomes a statement. For this conjunction of two statements to be true, each of them has to be true. So when is a negation P is true when x is less than or equal to 3. Okay, just take the negation of x greater than 3. Okay, so x less than or equal to 3, and then you have to intersect with the negation of q, which is x greater than or equal to 5. Okay, so you intersect x less than or equal to 3 and x greater than or equal to 5, and you don't have any intersection between those two intervals or sets. And again, you can easily draw the number 9s for these two intervals, and you find there's no intersection between them. So So there's no value of x which makes the open statement of fab true. So in other words, x, the set of x which make the compound open statement or statement true is the empty set. Okay, so that's that. Okay, so that's the first thing we talk, and then the next thing is called quantifiers. We use quantifiers very often in mathematics, and you have already seen them before, so the first quantifier is this. Okay, it's like a V, but there's a small bar inside of V. Okay, so that means for any x in a domain S. So let x be a variable with domain S, and let px be an open sentence. The expression of this is a sentence. Okay, and what it means is for any specific value of x in S, what is this px is. So in that way, you already picked up a specific value of x in this domain. So this p becomes a statement now. So when is it true? When is it false? It is true if p of x is true for each choice of x in S, and that is false if px is false for one or more choice of x in S. Okay, so if for any value of x in S, or for every or all of the x in S, this p is true, then this statement as a whole is true. But if there is one value of x or one element in S makes p of x false, then this expression is false. All right? It is a statement, so it has a truth value. So how do you know it's true or false? Then you have to determine, from this any particular problem. Okay. And we read this whole thing as for all x in S, p of x. All right. That's a statement. All right. Let's just look at some examples. Okay, we can do one more example actually. So just come back with the example before about triangles. Let S be the set of all triangles. So S is a set, and each element in this set is a triangle. So it's the set of all triangles, and let X be a variable with domain S. So X is just any triangle, that means. So let Px be the open sentence. All right. So that's an open sentence. The sum of the angle of X is 180. So that's an open sentence. And then the statement of any x in S, Px means, so remember this becomes sentence statement because you already pick a value of x from S. So it says for each or all of the x in S. So because we know S is the set of all triangles. So that means for all triangles, the sum of the angle of any triangle or all triangles is 180. So that's true. All right. So essentially, you can just say the sum of the angles of any triangle is 180, and that's obviously true. So we have two things in here. We have open sentence P of X, and then we have this quantifier, in the front, which specifies the value of X. So that the whole thing becomes a statement, and to determine whether this statement is true or not, then you have to check for any value of X in S, whether this P is true or not. So if that's the case, then P is true. If there's one value of X making P false, then this statement is false. All right. Okay, so we got 2 more minutes. I guess I'm going to stop here and continue from next time. I don't think we have time to do. Maybe we can finish this example. Okay. Again, we're talking about X, which is a variable with domain S. Okay. Which is the set of all triangles. Okay, so that's the same as previous example. And let Q be the open sentence we talked about before. One of the angles of X is a right angle. Okay, so that's an open sentence. It includes a variable X. If we write the statement of for any X in S, QX, okay, so it is statement now becomes to specify the value of X from S, any of them, okay. And then obviously, if you translate this sentence, it means for any triangle, okay. This is the domain of all triangles. So any triangle, one of the angles of any triangle is a right triangle. That's the statement Q now. If you plug in that X with any triangle, and that's false. Obviously, we have different types of triangles. Right triangle is just the one of those. So if you just pick up any triangle, then it's very you can easily find there's no triangle in that. There's no right angle in that triangle. Okay, so that's false. So this whole thing is false. Okay. Although it doesn't, give you, a specific value of X, it is a statement, and the statement is false. Okay, just make sure you understand what it means here. We talk about equilateral triangles or right triangles. It doesn't have any angle as triangle. So that's false. This statement is false. But however, if we let T be the subset of S containing all of right triangles, then you can write a statement of opposite any X in T QX. That's the true statement. If you just let X taking values from a subset of S, T, which is defined the set of all right triangles. Okay, so T is the set of all right triangles. So X is any of those. So then if we plug in this into the open sentence, Q1, it says one of the triangles of any right triangle is right angles. Obviously that's true. In a right triangle, you have a angle which is right angle. That's the definition of right triangle, actually. All right. So that's the end of today. Let me just